2008 National Electrical Code requirement for arc fault circuit interrupter, commonly known as AFCI, protection on 15 and 20 amp single pole circuits can potentially lead to overcrowding in breaker panels. This is because AFCI breakers tend to be larger than conventional circuit breakers, thus occupying more space within the panel. To address the increased space demands of AFCI breakers, manufacturers are actively involved in re-engineering both breaker panels and the breakers themselves. Some panels are being designed with more compact configurations, while others incorporate additional rows of breakers to increase capacity. In parallel, manufacturers have been developing slimmer AFCI breakers with the goal of minimizing their footprint inside the panel. A design concept involving breakers that plug into both the hot bus and the neutral bus simultaneously holds promise in mitigating the space limitations associated with AFCI breakers. By integrating the hot and neutral connections into a single device, the quantity of terminals and wires required can be reduced, potentially creating more space within the panel. However, it is crucial to acknowledge that such a design would necessitate comprehensive testing and certification to guarantee its safety and reliability. The design would have to adhere to the stipulations outlined in the National Electrical Code, as well as all relevant industry standards. Prior to investing significant resources in this design, it is essential to consider existing patents or pending patent applications pertaining to similar concepts. Consulting with a patent attorney is highly recommended to ascertain whether the invention is genuinely novel and potentially patentable. Obtaining a patent does not automatically guarantee widespread adoption of the design in the industry. Innovations in electrical products typically undergo a stringent process of testing, evaluation, and market acceptance before they become commonplace. The timeline for this process can span several years. The National Electrical Code, or NEC, is a comprehensive set of standards and guidelines for electrical wiring and equipment installation in the United States. It is updated every 3 years to reflect advancements in technology and safety practices. AFCI breakers are designed to detect arc faults, which are dangerous electrical conditions that can lead to fires. They work by monitoring the electrical current flowing through a circuit and tripping the breaker if they detect an abnormal arc. The requirement for AFCI protection in the 2008 NEC was intended to improve electrical safety and reduce the risk of fires. The National Electrical Code outlines specific requirements for the installation and use of electrical equipment and systems. These requirements are designed to ensure the safety of people and property. Article 210.12 of the National Electrical Code addresses arc fault circuit interrupter protection. The code specifies where AFCI protection is required in dwelling units. The 2008 edition of the National Electrical Code expanded AFCI requirements to include all 15 and 20 amp single-phase branch circuits supplying outlets installed in dwelling unit bedrooms. Subsequent editions of the National Electrical Code have further expanded AFCI requirements to include other areas of the home. These areas include family rooms, dining rooms, living rooms, parlors, libraries, dens, bedrooms, sunrooms, recreation rooms, closets, hallways, and similar rooms or areas. The purpose of these requirements is to provide enhanced protection against electrical fires. AFCI breakers are more sensitive to arc faults than traditional circuit breakers. They are designed to detect and respond to a wider range of arc fault conditions. There are two main types of AFCI breakers: branch feeder AFCI breakers and outlet branch circuit AFCI breakers. Branch feeder AFCI breakers are installed in the electrical panel and protect the entire branch circuit. Outlet branch circuit AFCI breakers are installed at the first outlet on the branch circuit and protect the remainder of the circuit. The National Electrical Code allows for the use of either type of AFCI breaker to meet the requirements of Article 210.12. When installing AFCI breakers, it is important to follow the manufacturer's instructions and the requirements of the National Electrical Code. The breakers should be properly labeled and tested to ensure that they are functioning correctly. Overcrowding in electrical panels can create a number of problems, including difficulty in accessing and working on the electrical system, increased risk of electrical shock, and reduced ventilation, which can lead to overheating and premature failure of electrical components. To avoid overcrowding, It is important to carefully plan the layout of the electrical panel and to use space-saving components such as slimline breakers and tantum breakers. It is also important to avoid overfilling conduit and junction boxes. The National Electrical Code provides guidelines for determining the maximum number of conductors that can be installed in a conduit or junction box. Re-engineering of breaker panels and breakers is an ongoing process driven by the need to improve safety, performance, and efficiency. Manufacturers are constantly developing new and innovative products to meet the evolving needs of the electrical industry. Some of the key trends in breaker panel and breaker re-engineering include miniaturization, increased functionality, and improved communication capabilities. Miniaturization is the process of reducing the size and weight of electrical components. This is particularly important in breaker panels, where space is often limited. Manufacturers are using new materials and manufacturing techniques to create smaller and more compact breakers and panels. Increased functionality refers to the addition of new features and capabilities to breakers and panels. For example, some breakers now include built-in surge protection, ground fault protection, and arc fault protection. These features can help to improve safety and reduce the risk of electrical fires. Improved communication capabilities refer to the ability of breakers and panels to communicate with other devices and systems. For example, some breakers can now communicate with smart home systems, allowing users to monitor and control their electrical usage remotely. The design of a breaker that plugs into both the hot bus and the neutral bar has the potential to reduce the number of wires and terminals required in the electrical panel. This can help to save space and simplify the wiring process. However, it is important to ensure that such a design meets all applicable safety standards and is properly tested and certified. Patent considerations are an important factor to consider when developing new electrical products. It is important to conduct a thorough patent search to determine if there are any existing patents that could potentially block the development or commercialization of the new product. It is also important to protect any new and innovative aspects of the product by filing for a patent. The timeline for developing and commercializing a new electrical product can vary depending on the complexity of the product and the regulatory requirements that must be met. It typically takes several years to bring a new electrical product to market. Innovations in electrical products typically undergo a rigorous process of testing, evaluation, and market acceptance before becoming mainstream. This process can involve extensive laboratory testing, field trials, and feedback from customers and industry experts. The NEC provides a comprehensive set of standards and guidelines for electrical installations. These standards are designed to ensure the safety of people and property. The NEC is updated every 3 years to reflect advancements in technology and safety practices. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It is essential for electrical contractors and installers to be familiar with the NEC and to follow its requirements carefully. Electrical safety is of paramount importance. Electrical shock and arc flash hazards can cause serious injury or death. It is important to take precautions when working with electricity, such as wearing appropriate personal protective equipment, using insulated tools, and following safe work practices. Regular inspection and maintenance of electrical systems can help to prevent electrical hazards. It is also important to educate people about electrical safety and to promote safe practices around electricity. The evolution of electrical technology has been driven by the need to improve safety, performance, and efficiency. From the invention of the light bulb to the development of sophisticated electronic devices, electrical technology has transformed the way we live and work. The future of electrical technology is likely to be characterized by continued innovation and advancements in areas such as renewable energy, smart grids, and electric vehicles. These advancements will require a skilled workforce and a commitment to ongoing education and training. The electrical industry offers a wide range of career opportunities for people with different skills and interests. Electricians, electrical engineers, and electrical technicians are all in demand. These professionals play a vital role in designing, installing, and maintaining electrical systems. Education and training are essential for success in the electrical industry. Apprenticeship programs, technical schools, and colleges offer a variety of educational opportunities. Continuing education is also important to stay up to date with the latest technologies and safety practices. The electrical industry is constantly evolving, and there is always something new to learn. By staying informed and embracing new technologies, electrical professionals can make a significant contribution to society. The design concept of having breakers that plug into both the hot bus and neutral bar represents an innovative approach to addressing the challenges of space constraints in electrical panels, particularly with the increasing adoption of AFCI breakers. This design aims to streamline the wiring process and reduce the overall footprint of circuit protection devices within the panel. Firstly, it is crucial to understand the current configuration of typical circuit breakers and their connections within an electrical panel. Standard breakers are designed to connect to the hot bus bar, which provides the energized conductor for the circuit. The neutral conductor from the circuit is then connected to a separate neutral bar within the panel. This configuration requires separate terminations for both the hot and neutral conductors, contributing to the overall clutter and space utilization within the panel. The proposed design seeks to consolidate these connections by integrating both the hot and neutral terminations into a single breaker unit. This would eliminate the need for a separate neutral connection, potentially reducing the number of wires and terminals within the panel. Secondly, the potential benefits of this design extend beyond simply saving space. By streamlining the wiring process, the design could also reduce the time and labor required for installation. This could be particularly advantageous in large-scale projects when numerous circuits need to be installed. Additionally, the consolidated design could potentially improve the reliability of the connections by reducing the number of points of failure. Thirdly, the implementation of this design would require careful consideration of several technical factors. The breaker would need to be designed to safely and effectively conduct both the hot and neutral currents. This would require appropriate insulation and conductor sizing to prevent overheating and ensure electrical safety. The design would also need to incorporate robust mechanical connections to ensure that the breaker remains securely attached to both the hot bus and neutral bar. Fourthly, the design must comply with all applicable safety standards and codes, including the National Electrical Code. This would involve rigorous testing and certification to ensure that the breaker meets all requirements for safety and performance. The testing process would need to verify that the breaker can withstand various fault conditions, such as short circuits and overloads, without posing a hazard. Fifthly, the integration of AFCI functionality into this consolidated breaker design would be a significant enhancement. AFCI breakers are designed to detect arc faults, which are dangerous electrical conditions that can lead to fires. By incorporating AFCI protection into the breaker, the design would provide an added layer of safety for the electrical system. Sixthly, the manufacturing process for this type of breaker would need to be carefully controlled to ensure consistent quality and reliability. The materials used in the breaker would need to be selected for their electrical and mechanical properties, as well as their resistance to environmental factors. The manufacturing process would also need to incorporate quality control measures to detect any defects or deviations from the design specifications. Seventhly, the market acceptance of this design would depend on several factors, including its cost, performance, and ease of installation. If the breaker can be manufactured at a competitive price and offer superior performance compared to existing breakers, it is likely to be well received by the electrical industry. However, it is important to educate electricians and contractors about the benefits of the design and to provide clear and concise installation instructions. Eighthly, the patent landscape surrounding this type of design would need to be carefully evaluated. A thorough patent search would need to be conducted to identify any existing patents that could potentially block the commercialization of the design. If any relevant patents are identified, it may be necessary to negotiate licensing agreements or to design around the patented technology. Ninthly, the long-term reliability and durability of the design would need to be demonstrated through extensive testing and field trials. This would involve subjecting the breaker to various environmental conditions, such as temperature extremes and humidity, to assess its ability to withstand these stresses over time. The testing would also need to verify that the breaker maintains its performance characteristics throughout its expected lifespan. Tenthly, the development of this type of breaker would require a multidisciplinary team of engineers with expertise in electrical engineering, mechanical engineering, and materials science. The team would need to work collaboratively to address the various technical challenges associated with the design and manufacturing of the breaker. In summary, the design concept of having breakers that plug into both the hot bus and neutral bar holds significant promise for improving the efficiency and safety of electrical installations. However, the successful implementation of this design would require careful consideration of various technical, economic, and legal factors. It would also require a strong commitment to innovation and a willingness to invest in research and development. The goal is to reduce the number of terminals and wires needed, potentially freeing up space in the panel.